Welcome back. I've just got a last two examples for us to work through with more related rates problems. The second last problem that we've got for the day involves these two planes, and they're flying. One of them is flying towards the town, and one of them is flying away from the town. And so, as I'm reading the story, I'm going to start making a little bit of a picture here. I've got one plane is flying towards a town from the north. So here I'm going to start off with making a little dot for my town. And then here's my plane that's going to be somewhere in the north. And this is the plane that's traveling towards the town. So it's heading in that direction. And that's at a speed of 200 kilometers per hour. And then I've got this second plane, which is over here. So this is plane number one. And here's plane number two. And this plane number two, this is heading away from the town. It's heading towards the east, so going in that direction at a speed of 300 kilometers an hour. And we want to know how fast is the distance between the two planes changing. So the distance between the two planes, that's this distance. I'm going to call this capital D. Using a capital D because we're using little d already in dy dx and things like that. So I don't want to have little d showing up for to mean distance because that'll just wind up being confusing. If I'm thinking about what I've got though, since the planes are traveling north-south and east-west, then things are meeting up at 90-degree angles. So it is looking like another Pythagorean equation kind of a moment. If I'm thinking about x being the distance between the town and plane number two, and if I'm thinking about y being the distance between the town and plane number one, then I do have an equation that I can use. I can say that x squared plus y squared is equal to capital D squared. And as far as the rates of change that I've been given, this first plane is getting closer to town. It's heading downward. In other words, the change in the y value is going to be something negative. So since that first plane is getting closer to town, its speed is going to be negative 200 kilometers an hour. So dy dt is negative 200. And that's because my y values are getting smaller and smaller and smaller, closer to town. For the second plane, on the other hand, it's getting further away from town. The x values are increasing. So for its speed being 300, that's going to be a positive 300 because the x distance is increasing. And we also want to know how fast is this distance changing between the planes when the first plane is 300 kilometers north. So in other words, the distance for y is 300. And for the second plane, it's 400 kilometers east of the town. So in other words, the second plane x value is 400. Okay, so we're pretty much ready to go because we've got our equation, x squared plus y squared equals d squared. And now we can differentiate both sides with respect to t. So the derivative of x squared, that's 2x, and derivative of x is dx dt. The derivative of y squared is 2y, and the derivative of y is dy dt. And the derivative of d squared is 2d, and the derivative of d is dd dt. I'm going to put a little star here for a moment because I'm going to need to come back to this. I notice that I've got, again, not quite everything. I've seen this happen a couple of times now where I don't have all the information given at the start. I know what x is and dx dt is. I know what y and dy dt is. I'm looking for the change in d with respect to time, d dt, but I need to know what d is. So actually, I have to do a little bit of side work to figure out the question of what is d when x is 400 and y is 300. So this is where I'm going to need to go back to my original equation, x squared plus y squared equals d squared. And I'm going to need to put in my 300 for y and my 400 for x. So let's go do that. So putting in x, 400 and 400 squared, that's 160,000. Y squared, 300 squared, that's 90,000. And that's equal to d squared. So 250,000 is d squared. And same as before, although technically there's plus or minus for the square root, because capital D is the distance between the two planes, that distance is going to be some sort of positive number. So I'm only going to take the positive square root, and so my distance is 500. So at that point, when the one plane is 400 kilometers to the east and the other is 300 kilometers to the north, the planes themselves are 500 kilometers apart from each other. Okay, so now we'll go back to our original question. And so from our little starred equation that we had 2 times x times dx dt plus 2 times y times dy dt equals 2 times d dd dt. And now we can just put in everything that we have for the change in distance with respect to time times 2d. D is 500, so we'll have 2 times that, or 1,000 dd dt. And then now we'll put everything else that we have in. We've got our 2 times x times dx dt. X was equal to 400 and dx dt was positive 300. So that gives me 240,000. 2 times y times dy dt. Y was equal to 300 and dy dt was negative 200. So that gives me negative 120,000. And so we get 120,000 equals 1,000 dd dt, or dd dt is 120. So that means that the distance between the planes is increasing. And it's increasing at a rate of 120 kilometers per hour. And there we go. So we've found out that when these two planes are traveling in this way, one going to the east, one heading southward from a northward position, at that point, those two planes are actually getting further apart. So even though one plane's getting close to the town, the other one, since it's going away from the town, that means the distance between the two planes is increasing. Okay, one last one. We've got a spherical balloon, and we've got water being pumped in at a rate of 1,900 centimeters cubed per minute. So a couple of things just to mention, of course. So we've got a balloon, and if we're imagining your sort of typical balloon, it's going to be something that is a sphere. And so for a sphere, we know that there's two formulas important to us, one for volume and one for surface area. The first part that we're being told about the water being pumped in, this 1900 centimeters cubed per minute is a change in the volume with respect to time. So we know that at least for this balloon, dV dt is going to be positive 1900 centimeters cubed per minute. And what we're looking for is how is the surface area changing? So what is the change in the surface area when the balloon has 1,000 cubic centimeters of water in it? And 1,000 cubic centimeters of water is a volume amount. So when the volume is 1,000, We also want to know how is it changing when the volume is 2,000. So actually I've got two little problems to solve. We're running into a problem here with this one though, because if you're thinking about volume and surface area, those two aren't related to each other in the same equation. I have a formula for volume. Volume is 4/3 pi r cubed. And I have a volume for surface area, which is 4 pi r squared. And so the problem is that I don't have an equation where I have volume equals something just involving S. But conveniently enough, I can do a little bit of a workaround here. I'm going to start with my volume equation for just a minute, and I'm going to differentiate both sides with respect to time. So on the left side of the equation, you'd have dv dt, and you'd have 4/3 pi r cubed. The derivative for that, the 4/3 pi would stay where they are. The 3 comes down, power is reduced by 1, dr dt. Or in other words, we would have dv dt is equal to 4 times pi r squared dr dt. And if I did the same thing for the second equation, I would do s equals 4 pi r squared. For its derivative, I would have ds dt for the derivative of s with respect to time. And 4 pi, we'll keep that where it is. And the derivative of r squared would be 2r. And the derivative of r, dr dt. So that would give me my change in the surface area with respect to time being 8 pi r dr dt. Okay, so where are we going to go from here? We're looking to solve for what ds dt is, and we want to solve for it when our volume is 1,000 or when our volume is 2,000. So what I need to do is come up with some sort of way to figure out how to get a derivative of surface area with respect to time that doesn't require me to know dr dt. And conveniently enough, you can see I've got, for both of my derivatives, they both involve dr dt. So my plan is I'm going to take my first equation, the one that involves change in volume with respect to time, and I'm going to solve for dr dt, and then I'll substitute that into my second derivative equation that I've got going on over here. So from that first equation, from number 1, I can rewrite this and say the change in volume with respect to time divided by 4 pi r squared is dr dt. And then I'll substitute that into my second equation. And for that one, I had that ds dt was 8 pi r times dr dt. And dr dt, we're replacing that with dv dt over 4 pi r squared. And then things clean up pretty nicely after this because, of course, the pi and the pi will cancel, the 4 and the 8 will cancel, the r and the r will cancel. So we'll be just left with 2 times dv dt over r. And that is ds dt. So now we actually have what we needed, which was the derivative of s with respect to time, also in terms of the derivative of volume with respect to time. We'll also notice here that we don't still have everything that we need, because it said, and I'm going to have to circle back here, we are looking for ds dt for particular points in time for particular volumes. So we actually need to know, if we're taking a look at the equation that we have, it doesn't have a spot for us to stick in volume, it has a spot for us to stick in radius. So on the side here, we might need to do a little bit more side work and say to ourselves, and this is for the two little bits of volume, if the volume is 1,000, what is the radius? Well, I know volume is 4/3 pi r cubed. And if we solve for when is volume equal to 1,000, we'd wind up finding for ourselves that r cubed would be 750 over pi. And so that means r is the cube root of 750 over pi. And then I could do the same sort of a thing with the volume being 2,000. So if I were doing the volume being 2,000, then instead of us having volume equal to 1,000, I would have volume equal to 2,000. And instead of it being 750 over pi for r cubed, it would be 1,500 over pi for r cubed. And so r would be cube root of 1,500 over pi. So I've got actually my two values for r that I can figure out. For the volume being 1,000, it's cube root of 750 over pi. For 2,000, it's cube root of 1,500 over pi. Okay, so now let's go back and actually solve our problem. So the big question that we wanted to find out was, what is ds dt? So for the first problem, when the volume is 1,000, we figured out at that point the radius would be cube root of 750 over pi. And so now we can figure out what we have. ds dt is 2 times dv dt. dv dt was 1,900, so 2 times that is 3,800, and divided by cube root of 750 over pi, which, when I work that out, that is about 612.5564. So that means the surface area is increasing at a rate of 612.5564, and we were measuring things in terms of centimeters for distances, so that would be centimeters squared, and time was being measured in hours, so centimeters squared per hours. And then we can say the same sort of thing about when volume is 2,000. The radius was cube root of 1,500 over pi. And then same sort of thing, we can find the change in our surface area by putting in what we know for dv dt. So 2 times 1,900 is 3,800, and divided by r, that cube root of 1,500 over pi. And that turns out to be about 486, thereabouts. 486.18676. Or rounding off to 4 decimal places, 0.1868. So again, that means that our surface area would be still increasing. In this way, it would be a rate of 486.1868 centimeters squared per minute. Or sorry, centimeters squared per hour, rather, because of course time was being measured in hours, and so our surface area is being measured in centimeters squared per hour. That's our rate of change of surface area.